Today we are going to discuss Zeeman effect and Paschen Back effect under atomic molecular physics. So both these effects are due to the presence of magnetic field. So we'll start with the Zeeman effect and then we'll go to Paschen Back effect. So what is Zeeman effect? We know that Zeeman effect is the splitting of spectral lines in the presence of, this is important, so in the presence of weak magnetic field. So weak magnetic field. So we have two kinds of Zeeman effect. One is the normal Zeeman effect. And other one is the anomalous Zeeman effect. Let me change the color here, and this color palette is here. It's here. So normal Zeeman effect we observe when we have your S is equal to 0, that is the spin quantum number is 0. And anomalous is observed when the spin quantum number is not equal to 0. The Zeeman spectra has components which are known as pi components and sigma components. So pi component, the polarization means the direction of the electric field, the polarization is parallel to the magnetic field. So that is the pi component, and the sigma component, the polarization is perpendicular to the magnetic field. So we go to first normal Zeeman effect. So the Zeeman effect is due to the interaction of the orbital magnetic moment with the external magnetic field. So this will give rise to a shift in the energy which is given by delta E. And so delta E will be minus mu L, which is the magnetic moment due to orbital electron and the orbital motion of the electron, and dot B is the external magnetic field. So here from immediately we get this term E H bar by twice M divided into ML B. So this we know, I have not written it. So this is the Bohr magneton. Okay. So from there we can immediately get that. So what we get is the delta of 1 by lambda. And what is delta by lambda? Is the shift in the reciprocal of wavelength of the spectral line with respect to the original line. Okay. So that is equal to EB by 4 pi MC times delta ML. That is the change in the value of ML. And by selection rule, delta ML can be only 0 or plus minus 1. That's it. So with this knowledge, so we have two energy levels. Say 1D2. So this is 1D2. So we have 1D2 and we have 1P1. So these energies, for these two energy levels, there is a transition given by this line. But when magnetic field is switched on, what happens is 1D2 is split into 5 energy levels. So degeneracy is broken corresponding to the Z component of the orbital angular momentum. So plus 2 to minus 2. And here this is broken into 3 components, 3 levels from corresponding to the Z component of the orbital angular momentum. So that is from plus 1 to minus 1. So now we can see, taking into account these selection rules, so we will have these sets of transitions. So these sets of transitions, which we will, this corresponds to delta ml changing to delta ml is equal to minus 1. So they correspond to one particular wavelength. This corresponds to delta ml is equal to 0, and this correspond to delta ml is equal to plus 1. So one line is split into two further lines. So this line, this was the original wavelength. So that wavelength is there, and this wavelength is there, and now we are having two more wavelengths. One is this one, and the other one is this one. So this is the pi. This transition is the pi component, and this set of transition is this is the sigma component, and this is also the sigma component. So this is the normal Zeeman effect due to normal Zeeman effect in the transition 1d2 to 1p1. So both are singlet states, and so you have normal Zeeman effect, this and this. Now we go to anomalous Zeeman effect. So anomalous Zeeman effect is when we have spin quantum number not equal to 0. So in that case, we will see that the energy shift is now, important thing about anomalous Zeeman effect is now that we have a total angular momentum quantum number j. So the interaction between the magnetic moment due to j and b is, of course, minus mu j dot b, and immediately I can write this thing as in terms of Landry factor. So Gj into Eh bar by twice m mj into b. So this is my, what is called, this is the bone magneton, and the allowed transitions are, delta mj should be 0 plus minus 1, and this transition mj is equal to 0 to mj is equal to 0 transition is allowed only when the delta j is not equal to 0. If delta j is equal to 0, then this mj is equal to 0 to mj is equal to 0 transition is not allowed. Okay. So this is an example of anomalous Zeeman effect. So this is in sodium. So we have two lines. One is the D1 line, which is given by this D1 line, and this is the D2 line. So the D2 line is a transition from the state 2p3 by 2 to 2s half, and this D1 line is a transition from 2p half to 2s half. Now when magnetic field is switched on, what happens is the energy level is shifted corresponding to the value of mj. Okay, so these are the values of mj, z component of mj. So 3 by 2, half, minus half, and 3 by 2. And for 2p half, the energy level is shifted according to the z component of the value of mj. So it will be, here it will be half and minus half. And here also for 2s half, the j component has quantum number half. So we have the two values, plus half and minus half, z component. And now we can see this. So these blue transitions, what we see, the blue transitions are from what was the previously 2p3 to what was previously 2s half. Now that transition D2 line is now broken into how many? It's now composed of 6 lines. And all these transitions take place according to the rule that we had just discussed. Similarly, the D1 line is now broken into into the red components. So, and this is what we observed through the spectrometer once we switch on the magnetic field. So instead of one D1 line, you are seeing 4 lines. So instead of D2 line, you are seeing 6 lines, and all these transitions are taking place according to the selection rules. And when you are calculating the shift in energy levels, you need to calculate these, right? So you have to calculate for 2p 3 by 2, you can find J, which is 4 by 3. The Lambda factor for 2p half is, okay, so you can also calculate what is the Lambda factor for this. So this I have not done here. So 2, then S, and then we have half. This you can calculate. This is singlet state. So this is what is the, so if you want to exactly find out the wavelength of the transitions, you have to know the Lambda factor. So you can calculate what is the, is equal to, is equal to, what's the value? Okay. So we go to the problem. So in a normal Zeeman effect, in a normal Zeeman effect, normal Zeeman effect experiment using a magnetic field of 0.3 Tesla, splitting within the components of a 660 nanometer is how much picometer? So we have to find the distance between the components. That is, what we have to find out is delta lambda. Okay, so delta lambda, we will start with this expression which we know. Delta 1 by lambda is this. So in this case, we want to find the difference between consecutive lines. So delta ml should be 1. And delta ml is equal to 1 means, from here, delta lambda, this is the main component is given 660 nanometer. So delta lambda is actually, we know that delta 1 by lambda is equal to minus 1 by lambda square into delta lambda. That's it. So lambda, this is given, this thing is given in the problem, and so we can easily find delta lambda. Go to the next problem. The spectral line corresponding to an atomic transition from J is equal to 1 to J is equal to 0 J is equal to 1, so these states splits into a magnetic field in a magnetic field of 0.1 Tesla into 3 components. So this J is equal to 1 to J is equal to transition is there without magnetic field. So there is a one line. When the magnetic field is switched on, it splits into 3 components, and these components are separated by 1.6 into 10 to the power minus 3 angstrom. If the zero field spectral line corresponds to 1849 angstrom, show that the G factor corresponding to J is equal to 1 is almost 1. So this is very similar. So here we again use this standard expression, delta 1 by lambda is equal to G ray EB by 4 pi MC. So delta lambda is given here, lambda is given here. So what we have to find out is this. So we have to find out this thing. B is given, mass of the electron we know 9.1 into 10 to the power minus 31 kg, velocity of light we know, and electronic charge also we know. Okay. Or you can, if you know Bohr magneton, then value of Bohr magneton, then you have to know only the you have to know only the value of C. Okay, so this problem is done. So the number of sublevels, and this is the next problem. So number of sublevels for D half. So this is all spectroscopic notation. So the number of sublevels, this thing is split in a weak magnetic field, is how much? So you might be tempted that this, if so, it's anomalous Zeeman effect. So this is the value of J. So it will be split according to the Z component of J. So there will be 2 components. But if you calculate the Lagrange factor, you convince yourself actually it turns out to be 0. So actually there will be no splitting. Okay, the number of sublevels is split in a, so it's split in a weak magnetic field is number of sublevels is split is basically there is no splitting. There will be only one, the original line will be, only the original line will be present and there will be no further splitting. This you can do on your own. Show that the transition from 3D2 to 3P1. So these are 2 levels, energy levels, 2 states, and there will be a transition between these 2. So when a magnetic field is switched on, you have to show that this is split into 9 components under the influence of a weak magnetic field. So this is, so you have to just do it. So this one will have break into, so this one will be split into 5 energy levels, this one will be split into 3 energy levels, and you have to calculate the Lagrange factor for this one as well as for this level. Okay, and if Lagrange factor is not 0, then it will be split into 5 and this will be split into 3, and then using the selection rule you have to find out the transitions. So now we go to Paschen Back effect, which also happens to be, so let me change the color here. So it happens, Paschen Back effect is also happens in the presence of magnetic field, but there is a very important difference. it has to be a strong magnetic field. And what happens, the magnetic field decouples S and L, decouple, and they couple only with the magnetic field separately. So there is no J here, there is no total angular momentum quantum number is not there. So a shift in the energy level in the presence of magnetic field is mu L plus mu S is the total magnetic moment, one due to orbital motion and one due to spin dot B. And you can easily see, you can write this as Bohr magneton ml plus twice ms into B. So this ml plus twice ms is actually, this thing will determine the shift in the energy. Again, so the selection rules are delta ml is equal to 0 plus minus 1 and delta ms is equal to 0. Now we'll look at an example and then this will make things clear. So now we have two levels. So initially, like we will not mention the angular momentum here, or the angular momentum here, because this angular momentum is not valid in this Paschen Back effect. So what happens? So when the magnetic field is switched on, so initially, like we had this kind of, we had seen D1 and D2 lines. Okay, so we had seen this, this D1 and D2 lines, 2p3 by 2, 2p half, etc. And we have weak magnetic field is switched on, and we have this. Now, but if a strong magnetic field is switched on, then what happens? That is what we are going to see. So for strong magnetic field, so this is my now 2p state. So 2p state has L is equal to 1, orbital quantum number is 1, and spin is half. So the orbital quantum number, and this is the number of levels. So for L is equal to 1, it will be split into 3 levels, and for spin half, it will be split into 2 levels. So we will have 6. So you can see what are the values of ml: 1, 0, and minus 1. And for 1, suppose 1, and what are the possible values of ms? It will be either half or it will be minus half. For again, in this case also, suppose ml is 0, in that case also this z component of the spin can only be half or minus half. For minus 1, it can be half minus half. So ml plus twice ms. So in this case, when the combination is 1 and half, then ml plus twice ms is 2. And when ml is 1 and ms is minus half, the ml plus twice ms is 0. Similarly, for 0 and half, ml plus twice ms is 1, and for 0 minus half, ml plus twice ms is minus 1. So like that, we have written down the values of ml plus twice ms for each combination. So here for minus 1 and half, it is 0. So like that we have done. For the other one, it is minus 2, here it is 1, here it is minus 1. And here now you can see that corresponding to this, here under 2p, this one, there are 2 zeros. So these two levels, there will be no shift and they will lie at the original energy level. So there will be no shift for these two levels, and that is -1 and half and 1 and -half, they will be at the same energy level and there will be no shift. So if you draw, again you see the 2p will have, there will be energy shift. So there are 6 components, so we have done the 6 components. So 1, 2, 3, 4, 5, 6, and against each level I have written down the ml and ms. So what I have written down is ml and ms values. Okay, ml and ms values. And for only for these two, as I discussed before, these two are at the same energy level, -half and half and 1 and -half, and these are at the same energy levels and they have not shifted from the original level. And again these two, and here I have drawn for 2s. For 2s also you can see, for here L is equal to 0 for 2s and spin quantum number is half. So number of levels for L is equal to 0, it will be 1, and for L is equal to half, there will be 2. So 1 into 2 is 2. So ml can take only one value, 0, whereas ms can take the values half or -half. So corresponding to the two sets, 0 and half and 0 and -half, we have the values 1 and -1 for ml plus twice ms. So from here you can draw the transition, you can figure out the transitions. So there will be, there will be 1, 2, 3, 4, 5, 6. So there will be 6 transitions. So initially there was from 2p half, there were two transitions. Okay, so initially we had 2 transitions, right, D1 and D2. Now because of Paschen Back effect, what we have 6 transitions, and these 6 transitions you can draw yourself. How? Just remember you have to remember the transition or selection rules. Delta ml is equal should be 0 and plus minus 1, and delta ml should be 0. So this is Paschen Back effect. So from the next lecture onwards, we will do molecular spectroscopy. So thank you.